Hello everyone. So, this is the third lecture of week 5. We are learning about Newton's method. Recall that in the previous two lectures we first learned the general form of Newton's method, learned some examples, and we also mentioned that the order of convergence of Newton's method is actually 2, this is quadratic convergence, but that actually comes with a drawback, which is there is no global convergence for Newton's method, it is only locally convergent, that is it converges if x naught is close enough to x star, otherwise it may not converge. Okay. So, we also saw an example, square root of x1 squared plus 1 plus square root of x2 squared plus 1. So, we also mentioned two other issues for which we will see some examples now. Okay. So, the second issue that I mentioned is that the descent direction that we chose minus hk inverse gk need not be a descent direction if hk were not positive definite, right. So, we saw that if it were positive definite, then it is certainly a descent direction. So, if it is not positive definite, it may turn out that minus hk inverse gk need not be a descent direction. Okay. So, there is a simple example which I can give it analytically. Okay. So, what is that? So, let f of x1 x2 equals x1 squared minus x2 squared. Okay. So, this is quadratic function, but with h not being positive definite, h is actually indefinite, right. So, and let us take x0 as 1 comma 2. Okay. So, so in this case you can see that so f of x naught is actually 1 minus 4, which is minus 3. Okay. Now, let us see what is x1, x1 is x0, that is 1 comma 2, right, minus h inverse is h is, if you recall, it is 2 0 0 minus 2. So, the inverse is half 0 0 minus half h inverse into gk. So, gk is 2x1 and minus 2x2. So, 2x1 is 2 and minus 2x2 is minus 4. So, that is 1 2 minus 1 and 2, which is 0 0, right. So, you can see that f of x1 is actually 0 and that is greater than f of x0, right. So, I started with a point where f of x was minus 3. After applying the algorithm, I have reached at an x where f of x is actually 0, which is greater than f of x0. Okay. So, here you have an example of so the fact that hk minus hk inverse gk need not be a descent direction if hk is not positive definite, but you may still be not be satisfied because of the following reason, that this function does not have a minimum, right. So, what is the minimum of this function? It is minus infinity. So, you put 0 comma infinity, x1 equal to 0 and x2 equal to infinity, right. So, f of x1 x2 is minus infinity, right. So, for this function the minimum does not exist. So, you might think that maybe that is the reason why we got an example where minus hk inverse gk was not a descent direction, right. So, I will give an example where you have the answer, you know you have the answer, you know what the answer is, but you still end up with f of x1 greater than f of x0. Okay. The example is very simple, it is the same example that we are working for quite a long time. F of x equal to x1 squared e power x2 plus x2 squared e power x1, but x naught is not root 2, it is going to be minus root 2 minus root 2. Okay. So, let us do that, let us check what the answer is. Okay. Yeah. So, this is the example for this is the example that we considered. I am just going to make a small change, it is minus root 2 and minus root 2, and to prove to you that f of x is increasing, I am also going to print f of x here. Yeah, usually we do not print that, but since I want to show you that f of x is not of the form that we want it to be. Yeah. So, let us note this a little bit carefully. So, at 0, yeah, the iteration 0, it is the initial point, x0 is minus root 2 minus root 2, f of x0 is 0.9725. Okay. And at x1 you have moved to some other point, and f of x1 is actually 1.081, okay, which is greater than 0.9725, right. Okay. So, that is not the end of the problem. You can see that the convergence is not to the right answer 0 comma 0, okay, we know that the right answer is 0 comma 0, right, but it has converged to a very different point minus 2 comma minus 2, okay. And mind you, it is actually converged, because I mean it stops only when norm of gk is less than or equal to 1 e minus 6, and the norm of gk is actually less than 1 e minus 6, right. In fact, it is 0. Okay. I will show to you what actually happens. Okay. So, I have given an initial point, and it turns out that the algorithm, the Newton's method algorithm, has actually converged to a different point than, I mean, which is not the minimum. Okay. So, why was that the case? So, let us analyze what is actually happening analytically. Okay. So, let f of x1 x2 is x1 squared e power x2 plus x2 squared e power x1. Yeah. So, and we know that del f of x is 2x1 e power x2 plus x2 squared e power x1, sorry, and this is 2x2 e power x1 plus x1 squared e power x2, right, and h of x is 2 e power x2 plus x2 squared e power x1, 2x1 e power x2 plus 2x2 e power x1, 2x1 e power x2 plus 2x2 e power x1, and 2 e power x1 plus x1 squared e power x2, right. What happens at x1 x2 equal to minus 2 minus 2? Del f of x actually becomes minus 4 e power minus 2 plus 4 e power minus 2, which is 0, and similarly here minus 4 e power minus 2 plus 4 e power minus 2, that is 0. So, we actually have another critical point, okay, for this problem at minus 2 comma minus 2, okay. But I mean we should not stop saying that it is a critical point, we need to analyze whether it is a local minimum, local maximum, or a saddle point, right. So, let us do that for by checking what happens at h of x, right. So, this is 2 by e squared plus 4 by e squared, that is 6 by e squared, and this is minus 4 by e squared minus 4 by e squared. So, minus 8 by e squared, this is also minus 8 by e squared, and this is 6 by e squared. So, you can see that h of x, so yeah, I mean it is immediate that the determinant of h is negative. If the determinant of h is negative, that means in 2 dimensions the matrix is indefinite, right. So, this point x1 x2 equal to -2 is a saddle point. So, unfortunately, when we started with -√2 instead of converging to 0 comma 0, which is a local minimum, in fact the global minimum as well for this problem, it has the Newton's method algorithm has actually converged to a saddle point. Okay. So, that is a problem, and let me also show that that is not the case for conjugate gradient and gradient descent. Okay. So, I mean we have the algorithms for everything, so I can just modify the values and show you everything, right. So, yeah, so this is, if you recall, Fletcher-Reeves for the same function. So, I am going to use the same initial value. Let us check what happens to this algorithm. You can see that it converges to 0 comma 0, the actual local minimum in 22 steps. Okay. So, that is for Fletcher-Reeves, and if you go ahead to the gradient descent algorithm. Okay. So, again we have used the same function. So, I can just modify the initial point and check what happens. Okay. And yeah, so let us not plot anything, we will comment them out. Again it has taken 26 steps, slightly higher than Fletcher-Reeves. Fletcher-Reeves is usually a little bit faster than gradient descent. So, in 26 steps it has converged to 0 comma 0, which is the actual local minimum. Mind you, I have actually used the same initial point in all 3 algorithms. Okay. So, Newton's method has been faster usually, yes, that is correct, but because it has certain issues, for example, if we have a point where hk is not positive definite. Okay. So, I mean it turns out that yeah, I mean the algorithm has actually converged to a saddle point instead of the local minimum, and you also saw that the value of f of x was increasing from 0.975, it is 1.081, then 1.083 and so on, right, all because of the fact that if you blindly use minus hk inverse gk, yeah, you might actually end up having problems. Okay. Yes, so that is an example for this issue, that minus hk inverse gk need not be a descent direction. And the third, okay, computationally expensive is something that you can see by giving big matrices. Okay. But I would like to give an example where you end up with singular hk. Okay. So, I am just going to give a simple example. Okay. So, let f of x1 x2 is be x1 cube minus 3x1 square sorry 3x1 plus x2 cube minus 3x2. Okay. Simple. And I mean if you want to find which is the local minimum. So, del f of x is 3x1 squared or 3 into x1 squared minus 1 and 3 into x2 squared minus 1. So, 2 critical points sorry actually 4 critical points plus or x1 equal to plus or minus 1 and x2 equal to plus or minus 1. So, 1 1 1 minus 1 minus 1 1 and minus 1 minus 1. So, you have 4 critical points for this particular problem. We can also check h of x, which is 6x1 0 0 6x2, and so this is positive definite only when x1 x2 is 1 comma 1. Okay. So, yeah, positive definite only if x1 x2 equals 1 comma 1. Okay. So, 1 comma 1 is the only local minimum, 1 minus 1 and minus 1 1 are saddle points, and minus 1 minus 1 is local maximum. Okay. Fine. So, yeah, that is very clear analytically. Okay. Now, let us actually check what happens for different initial values, okay, for this particular example. So, mind you, this is all local minimum and local maximum, because the global minimum and global maximum does not exist. Okay. So, if x1 x2 is minus infinity, then the problem, I mean the function value is minus infinity, then and if x1 x2 is infinity, then the problem value is infinity, but I mean we are only trying to find local minimum and local maximum of this particular function. Okay. So, let us do that. Yeah. So, let me just copy down from here. So, this is yeah, an example for, I will just write example for singular Hessian. So, maybe yeah. So, yeah, the function is x naught cube minus 3 into x naught and x1 cube minus 3 into x1. Okay. So, this is 3 into x naught squared minus 3 and okay. So, this is small. So, let me just put it in the same line, 3 into x1 squared minus 3. Okay. And here again it is going to be very simple, it is just 6 into x0 comma 0 and 0 6 into x1. Okay. So, yeah, note that the answer is 1 comma 1. So, let me start with 0.5 0.5. Good. So, it has converged in 4 steps to the right answer 1 comma 1. Now, let me put minus 0.5 minus 0.5. It has converged to the local maximum minus 1 minus 1, that is because we are just asking the problem to find the critical point anyway, right. So, I mean it just converges to the nearest critical point, that is it. And let me try 0.5 minus 0.5, it actually converges to minus 1 1, which is a saddle point, okay, because it does not check whether the solution that it converges to is yeah, local minimum, local maximum or a saddle point. And similarly for 0.5 minus 0.5 as well, it will converge to 1 minus 1, which is again a saddle point. Okay. So, I mean that is also something that I wanted to illustrate, but I mean that was not the main illustration purpose. I wanted to give an example for singular Hessian, right. So, if you give 0 0, yeah, so there is an error, it says that you have got a singular matrix. Okay. So, when you have this in a practical problem that you encounter, just modify x and go ahead, or modify the algorithm, I mean consider variance of Newton's method or something of that sort. There is no other respite when the hk that you have is a singular matrix. Okay. So, yeah, I think it is good to keep that in mind, and we have actually discussed examples for all 3 cases where, I mean, for these 3 different issues that we might actually have, right. Alright. So, I mean these have solutions in the sense that we will consider variants of Newton's method to get around these issues. Okay. But before that, I want to I mean show you that the order of convergence of Newton's method is 2, okay, and that the Newton's method is indeed locally convergent. Okay. So, note that I just mentioned here that Newton's method is locally convergent, okay, without any conditions being specified, is not it. That means so there exists a delta positive for which when norm x naught minus x star is less than delta, the algorithm converges. Of course, even if this is true, there is a problem how to choose x naught without knowing x star, we understand all that, okay. But in case you choose x naught in this way, okay. So, if you are sufficiently close to x star, then I am saying that the convergence is guaranteed, is not it. That is again a tall climb and that needs a proof, okay. So, I am actually going to prove this theorem, okay. So, I will write down the theorem and write the proof now, okay. So, the theorem is, okay, consider a thrice differentiable function, okay. Yeah, this is one issue, I mean, so twice differentiable may not be sufficient, okay. Function f, okay. So, suppose we use Newton's method to minimize f. Then there exists delta positive such that norm x 0 minus when norm x 0 minus x star less than delta, then the method converges, okay, and converges with an order of convergence equal to 2, okay. So, yeah, so that is the theorem, and I will give you a proof now. So, I am going to give the proof when the domain of x is the real line, okay. So, that is n is equal to 1, okay. Extending the proof is not very hard, but it involves the 3 dimensional gradient, right. So, yeah, or rather the third order gradient which is 3 dimensional, right. So, the first order gradient is 1 dimensional, the second order gradient is 2 dimensional n cross n, right. The third order gradient is n cross n cross n, okay. So, I mean it involves those things. So, I mean that is the reason why I am actually avoiding I mean general n dimensional I mean discussion using general n dimensional functions, okay. But yeah, the proof goes through, let me tell you that. So, consider f r to r, okay. So, now how does xk plus 1 vary in that case, right. So, xk plus 1 is xk minus, so we say hk inverse which is actually f double dash, right, and yeah, so it is actually f double dash of xk inverse into f dash of xk, right, or xk minus, so if you yeah, f dash of xk is g of xk, right. So, g of xk by g dash of xk, right. So, yeah, so if I subtract x star on both sides, I have xk plus 1 minus x star equal to xk minus x star minus g of xk by g dash of xk, okay. And so, let me write down the Taylor's expansion for g of x star, okay. So, that will be g of xk plus g dash of xk into x star minus xk plus half g double dash of xk into x star minus xk the whole square. So, note that this is much simpler because I mean each of them is one dimensional, okay. So, otherwise I mean you need to be a little careful about dimensions and yeah, so and actually if g itself will be a vector, right, and g double dash will be a 3 dimensional matrix, okay, all right. So, fine. So, note that g of x star is actually 0, right. So, that is why I mean x star is the minimizer. So, g of x star has to be 0, okay. So, we have so if you divide the whole equation by g dash of xk, you will have minus g of xk by g dash of xk minus x star minus xk, that means plus xk minus x star plus sorry equal to half g double dash of xk by, so so let me write this as xk bar, so this is using the remainder form for some xk bar in the line segment connecting xk and x star, okay. So, yeah, so this will be g double dash of x bar by g dash of xk into yeah, x star minus xk the whole squared or xk minus x star the whole square, both are the same, okay. So, note that this quantity that you have here, right. So, that is actually xk minus xk plus 1 minus x star. So, you have xk plus 1 minus x star equals half g double dash of x bar k by g dash of xk into xk minus x star the whole square, okay. So, what about the absolute value of this? Very simple, this is just the absolute value and here as well the absolute value, right. So, I can take the absolute value just on both sides, nothing varies because of that, okay. So, yeah, let us keep this in mind that xk plus 1 minus x star is equal to half norm g double dash of x bar k by norm g dash of x k into xk minus x star the whole square, okay. So, you can actually I mean see how the order of convergence is 2, right. So, recall the definition for order of convergence, right, where is that, yeah, so yeah, this is the definition. So, we see that norm xk plus 1 minus x star by norm xk minus x star the whole squared is a constant, right. So, that is what we have here, right, norm xk plus xk plus 1 minus x star by norm xk minus x star the whole squared is a number, right, yeah. So, fine. I mean so a little bit of a heuristic is what I gave here, but I have still not I mean shown the local convergence, right. So, I have not shown that delta positive, I mean there exists a delta positive such that when x naught is close enough to x star, the method actually converges, right. So, I mean let me do that now. Okay. So, if let us say x naught is within yeah x star minus eta to x star plus eta. Okay. So, then let alpha 1 equal max x in x star minus eta to x star plus eta, sorry g double dash of x, and alpha 2 be min x okay. So, then x k plus 1 minus mod x k plus 1 minus x star is actually less than or equal to alpha 1 by 2 alpha 2 norm x k minus x star the whole squared. Okay. So, I have just found an alpha 1 and alpha 2 by restricting x naught to a small ball, okay. And we are still not done because we do not know if this would still converge, right, because we still want alpha 1 by 2 alpha 2 into x k minus x star to be less than 1, okay. Only then I mean I can be sure of the convergence, right. So, fine, we will consider an x k which satisfies this condition, right. So, that is, but this can be satisfied if x naught is chosen such that x naught minus x star is less than 2 alpha 2 by alpha 1, right. So, choose delta positive such that delta is less than the minimum of eta and 2 alpha 2 by alpha 1, okay. So, if you choose in such a way a ball I mean a value of delta in such a way that it is less than the minimum of eta and 2 alpha 2 by alpha 1, okay. So, then I mean you can see that mod x k plus 1 minus x star is less than or equal to some number into mod x k minus x star, and that some number is actually less than 1, okay. And you have also made sure that the convergence is quadratic, okay. So, that is actually the proof, okay. So, yeah, so that is a good result, that if you have any thrice differentiable function, then local convergence is guaranteed and the order of convergence is also equal to 2, okay. So, in the next lecture we will learn about some variants of Newton's method, like damped Newton's method, trust region method and so on, which avoids the issues that we have mentioned in yesterday's I mean in the previous lecture and today's lecture, okay. Thank you.